And I would also like to thank the group of Athens for hosting me, and especially Mr. Nagostopoulos for invitation. So as Mr. Nagostopoulos announced, so today I want to discuss about confinement and deconfinement transition with the zero-brane matrix model. And the key message I want to deliver is that one can actually use this model as a test example to study contents of M theory. So this work is based in appeared in arXiv under this number, and with my collaborators, which from now onwards we will be called ourselves as MC SMC from Monte Carlo string M theory collaboration. And in a nutshell, I would like to discuss my talk, how it will go. And I will start with the definition of these zero matrix models. Then I will discuss the holographic construction of these models and how the degrees of freedom organize themselves to produce gravity data. After this explanation here, then I would like to give some results that we have observed the confinement phase in the BFSS model, and trying to understand what is this confined phase. We propose that this could be related with an 11-dimensional Schwarzschild black hole. So this being said, let's start with the definition of the model. And this model appeared in many different places, and it is also known better nowadays by the name of BFSS, by the work done by Banks, Fischler, Senker, and Susskind in '96. So the model itself, it has a Lagrangian, which is of this form, and it consists of bosonic matrices, which I call here X, and fermionic matrices. So in this case, M runs from 1 to 9. So you have 9 bosonic matrices, while on the other hand, alphas run from 1 to 16. So one has 16 fermionic matrices. Now, this model appears as a dimensional reduction of super Yang-Mills theories, either in 4 dimensions or from 10 dimensions. And back in '88, a work by David, Hoppe, and Nicolai. So basically, they were trying to quantize the 11-dimensional supermembrane, and they proposed a very clever matrix regularization, and it turned out to give this Lagrangian. Now, approximately 10 years later, BFSS proposed this specific model as a non-perturbative formulation of M theory in a specific limit. Again, 2 years later, after the appearance of Maldacena duality, a work by Itzhaki, Maldacena, Sumensain, and Yankelowitz suggested that this model can be related to some geometry, which is known as a type 2A black zero brane in the 't Hooft limit. So today, of course, we will be focused into these 2 particular cases. So starting, I would like to introduce a little bit the case gravity duality such that everybody is in the same page. And I will assume basic knowledge from string theory. And Maldacena in '97 proposed that, so basically, a black p-brane in type 2A and type 2B string theory should be dual to p plus 1 dimensional super Yang-Mills theories with UN gates group. So this the equivalent should be that a black p-brane is dual to a bound state from the field theory point of view.
Excuse me, can I interrupt
Yes.
for a moment and ask a quick question?
Yes.
The duality is assumed to be exact at the quantum level. It has never been shown rigorously.
Yes.
Am I right? Okay.
Indeed, indeed.
Thank you.
This is classical, or let me say semi-classically. So currently it's under investigation if this is really the case or not.
Thank you.
And here the original example was for p equal 3, which back-reacted in a geometry of ADS 5 times S5. And this was dual to a CFT4, which is super Young-Mills in 4 dimensions. But in this particular case, we will discuss the case where p equals 0. So here we will have a black zero brane. And here we will have 0 plus 1 dimensional quantum mechanics, which will be basically matrix quantum mechanics. Now, of course, there are other models like the 1 plus 1 dimensional model, which have been studied by several people. But also there is the D-instaton model, known as the IKKT model. And many of you people who are in the audience did a great job to also, to understand it either simulation-wise or analytically. So diving in a little bit more for the case of when p is 0, the difference with the 4-dimensional case is that the tooth coupling in this case has dimensions of mass cubed. So indeed, we don't have a CFT, but one can construct a dimensionless coupling by dividing with suitable powers of energy. And from this, one can see that low energies correspond to strong coupling. Basically, this holds if we fix lambda. Otherwise, we can send lambda to be very large, and then we are getting the strong coupling between. Now, this specific case has a dual gravity interpretation known as the black zero brane in type 2A supergravity. And of course, there is a metric describing this object, and one can pursue a thermodynamic analysis based on the laws of quantum mechanics of black hole thermodynamics. And the scaling of the energy of this particular geometry is like this. Of course, we see there are some funny powers here, where this is because of the coupling has dimensions of mass cubed. And the temperature here is the Hawking temperature of this black zero brane. In addition, the radius of this black zero brane is proportional to 1 over the curvature, and demanding that this curvature to be small means that one demands the effective coupling to be large. But at the same time, one has to ensure that the dilaton in the horizon does not become big. So in order to have a valid type 2A P0 geometry, one has to take the limit where n goes much faster than the effective coupling. Now here, a work appeared by Itzhaki Maldacen, as we discussed in previous slides. We can see that there should be, if this description is correct, then keeping n, fixing n and pushing the coupling be large, there should be regions where we go to M-theory circles. And this can be motivated as follows. So indeed, we are in the P0 case, and we can imagine that we have a black hole which is boosted along the 11th circle, while on the other hand, we know that the 11th circle is related to the G string. Now, if we go back, the horizon, the dilaton here is G string, which furthermore is G effective. And taking G effective to be very large, the 11th dimension opens up. So one should try to understand this as going from like this direction corresponds to going to this direction here. And from the point of view of an 11-dimensional observer, this black hole here will appear to be small. So again, I remind that the dimension of the coupling is mass cubed, and basically when we think about the Larsen limit, one way to think about it is to fix lambda, where in simulations we fix lambda to be 1, and the dimension is temperature to be of order 1. Now the holographic construction, that the way it works is a little bit interesting, and it is given like this. So as I told, we have 9 bosonic matrices here. So M runs from 1 to 9, and its matrix is n by n. Now, according to Witten interpretation of bound states of D-branes, diagonal elements of this matrix can be thought as positions of these zeros, while non-diagonal elements as open strings connecting the D0 branes. This can be motivated also if you think as the entries, so the indices of the matrix as a sun pattern indices that describe strings beginning and ending on another brane. So again, each matrix here gives information for 1 dimension, but we have 9 matrices. We have information about a 9-dimensional space. So indeed, one can use this matrix model to do Monte Carlo simulations, and one can borrow techniques from lattice QCD, where this technique is quite established. Therefore, we have to simulate 0 plus 1-dimensional matrix quantum mechanics. And this is much easier than QCD because we have just 1 dimension. Now, this dimension is discretized in a lattice sense, and it is a parameter that we call time. And when one wants to understand the theory in finite temperature, you get the Euclidean picture when this circle, when this line is compactified to a circle, and the period is given as 2 pi inverse of temperature. The parameters that we control to understand the system simulation-wise is n, which gives information about how big the matrix is, S, which is the lattice point, the number of the lattice points, and of course the temperature, which is assigned again to this circle. So now I'm switching to discuss a little bit the confinement and deconfinement transition. And an order parameter to distinguish between these two phases is the Polyakov loop defined as this. Here P is the path ordered, while H is the gates field. Now, restoration or breaking of the U1 symmetry, which is a symmetry of the Polyakov loop, signals a phase transition from confinement to deconfinement. And this is a very well established problem in ADS5, process 5 holography, which is discussed indeed quite well in Magoo. Magoo is an agrammatism for Aharon, Maldacena, Hubsper, Oguri, and Oz, while also Aharon, Marsano, Mivala, Papadodimas, and Varamsto have discussed, they are discussing indeed quite well this picture. So the idea is that when the Polyakov loop is 0, we are in the confined state, which this bound state here can be understood as a graviton gas. On the other hand, when the Polyakov loop gets an expectation value, we have the confinement, and this is related to black holes. And in this specific case, is related to big black holes in ADS pi. Now, having built some intuition from this picture, we can try to understand the same problem for p equals 0. And for p equals 0, it is very well believed that the deconfinement phase corresponds to a black zero brane of type 2a supergravity. But it was not really expected, at least from this type 2a, to have confinement state. And if it would be, then what would be, how should we interpret this bound state? So it was not clear if this would exist in this case and what would be, how to think about it. So here I want to show that how we understand this thing in simulations. And in order to do this, I have a graph which on the x-axis is the Monte Carlo history, also the Monte Carlo time, while on the y-axis is the Polyakov loop. So we see here that the simulation starts from a case where p is approximately 0, and this is a confined phase, while after some time it transitions to p around p 0.5, and this is assigned to the deconfined phase. And the question we wanted to ask and understand is how can we understand, in what terms can we understand this bound state? Now, of course, this doesn't mean that this is a confined phase, but I will show later evidence that indeed we have a confined phase. So the idea, the expectations from gravity is that, yes.
Can I ask? I'm not sure if collaborators are allowed to ask questions, but you said this does not mean confined, does not necessarily mean confinement, but why do you say that? Or you want to really show that it goes to 0, or?
Yes, in a sense that here we see a transition, right? But we don't have a stable confined phase.
Okay. So you mean maybe you cannot exclude the possibility of lattice simulation artifact at this point.
Yes.
And you want
indeed.
to give better evidence. Okay.
Indeed. So from the gravity side, we expect that energy in the Polyakov loop is non-zero in every temperature, as it's seen from here. And this means that there should be deconfined. Along with the Polyakov loop, another parameter to distinguish this is the free energy. And when the free energy goes like n squared, it means that we are in the confined phase. But our proposal is that the confined phase should exist as well, which means that the energy should be 0, both the energy and the Polyakov loop. And later, as Masanori said, I will provide some evidence that indeed we have this phase here. So of course, there are many studies of the deconfinement phase given by an incomplete list of people here. And one interesting, at least for me, work was to try to reproduce the scalings of the supergravity. So here in this graph, there are many works done at finite n and not continuum limit, which is these lines here. But what is more interesting is the lattice points that go all the way here. And this is indeed large n and continuum extrapolation. So this was done in 2016 by my collaborators when I was not part of the group then. And indeed, as you can see, when one approaches the low temperature regime, one approaches the low energy regime, which means that this is strong coupling. And indeed, the supergravity prediction given by this line, this black line, is reproduced by fits done for the simulation points. Now, this simulation, the discrepancy here is because the fits that are used include alpha prime corrections. And another thing we're trying to understand now is that we even try to push to this direction. And currently this is under investigation. But here in the next slide, I want to provide some evidence that indeed we see the confined phase in simulations. So here, the two observables that are under consideration is the sum of the trace of the matrices squared divided by 10 for normalization purposes, given by blue, and the Polyakov loop given by the black line. So here we see that the Polyakov loop in these parameters, which is quite low temperature, fluctuates around 0. But this specific parameters is not really well under control, because you see here the growing of this observable, which means that one of the matrices starts growing. And this is related to the flat problem, to the flat direction problem of this BFSS. And basically this is due to the commutativity of the matrices. Because one can diagonalize simultaneously, then there could be eigenvalues escaping to infinity, and this is energetically without cost. But when one switches to larger n, we expect that that this bound state does not allow for runaway behavior, and this is even when we, for example, using larger n. So this seems to be much more stable. Here, I proceed a little bit more with the confined phase. And of course, this is just an example of evidence, and you can look into more details in our paper where we have much more evidence about these observables. So here on the left side is large n extrapolation at temperature 0.2, while on the right side we have continuum extrapolation. Now here, energy is denoted by red, and I want to pay attention to the deconfined phase. So if we would be in the deconfined phase, the predictions say that the energy should be 0.08, which if we look in this diagram, this would be here, while the continuum extrapolation tells us that energy is here. On the other hand, the Polyakov loop in the deconfined phase should be around 0.5, and if we look in the large n extrapolation, this would be somewhere here. But obviously, the Polyakov loop is not there. So as it turns out, energy is sensitive to the continuum limit, while the Polyakov loop is sensitive to large n limit. And from this, I hope that I can somehow convince you that we are not in the deconfined phase, but we are in the confined phases, since energy and Polyakov loop are 0, which is expected in the confined phase. So up to now, what I've shown is that we have observed the confinement phase in BFSS, and some a little bit more details is that below temperature 0.27, we've seen only confined states, while above 0.7, we have only seen the confined states. But in this particular case, for the BFSS model, the flat direction is not fully under control. So again, up to now, we can study either confined or the confined phase. But the question I want to ask now is that, can we see both simultaneously? And the answer will turn out to be yes. But for this, we have to use another model. Are there any questions so far before we continue? I guess not, so I'm continuing. So to understand, to study both phases simultaneously, we have to look in the BMN matrix model. So this is from the initials of Bernstein, Maldacena, and Astase in 2002. And what it basically does is to add some terms here in addition to BFSS, where BFSS are given by this axiom here, while the deformation terms are given by delta SP and delta SF for bosons and fermions. Now, before discussing about simulations, let's talk about a little bit more details about this model. And what it does is that it gives mass terms to bosons and fermions. In addition, it is interesting because this addition of the terms breaks the original SO9 symmetry, which is in this line. So here you see that I and J run from 1 to 9. So the model itself has an inbuilt SO9 rotational symmetry. But when we are adding these terms, you see that this group runs from 1 to 3. So it gives an SO3 rotational symmetry, while this group runs from 4 to 9. So it gives an SO6 rotational symmetry. So therefore, the symmetries break like this. And as we will see, we also have SU2 vacua, which can be represented as fuzzy spheres. So the BMN matrix model is a supersymmetric deformation of BFSS because it has some BPS states. And one can write the SO3 potential like this. And this potential is 0 if we assign the matrices with SU2 generators. This makes the flat direction to be lifted because the matrices do not commute anymore. And in addition to this, we have fuzzy sphere vacuum. So the SO3 part of BMN has fuzzy spheres, while the rest of the matrices have to be 0. Of course, this is classical vacua, and we should have quantum fluctuations. But in simulations, we were not much interested regarding this vacua because it is less well understood from the gravity side. So we wanted to focus a little bit more into the somehow trivial vacuum, which all the matrices are 0 plus quantum fluctuations. So again, the BMN matrix model has an effective coupling if we combine lambda, and here we have a mass square to the cubed. And when one wants to study the gravity dual, should take the G effective to be large. So this means either lambda to be large, but in simulations, we are fixing lambda to be 1. So we have to send mu to 0. But again, simulation-wise, this limit is not very attractive. It's not very easy to simulate. So the gravity dual is a deformation of type 2A black zero brane, a work done by Costa, Greenspan, Penedones, and Sandoz in 2014 revealed that the complexity of this gravity dual of the BMN matrix model is much more complicated than the BFSS. And in our case, we want to prove the gravity limit. So we can imagine that we are in a first order phase transition where the Polyakov loop and temperature are given like this. So we have 3 different temperatures, T1, T2, and Tc. But in simulations, what we always observe when we see a transition from confined to confined is Tc, what we say T critical. And indeed, we see here that there is a two-state signal, this green line, and again, there's again another one green line here indicating a two-state signal, which basically means that the simulation is spending equally well time in the confined phase. So here is the Polyakov loop, and spends the simulation spends equally well time to P around 0 and P around 1/2. So this means that we are in the confined and deconfined phase. We can observe them simultaneously. And what we also checked is we wanted to compare our results with perturbative calculations at n infinity, which is given by this line here, and also compare with gravity at large n, at n to infinity. Remember that as we send mu to 0, we should approach the gravity side because this G effective becomes large. So indeed, what we see here is that the gravity line is approached, but at some point we have deviations which can be understood as finite n corrections, because the simulations point here are specific. They have specific end and lattice spacing, while the gravity prediction is done at n to infinity. So now I want to again discuss how what we think that is going on in the phase diagram of this case. And when n is sent to infinity, we expect that the energy should go to 0 at any temperature. But here we propose that there is a separation between the deconfined phase and the confined phase with another intermediate phase, while all this, so the deconfined phase and the confined phase can be understood as minima, while the separating phase can be understood as a maximum of the free energy. And we will see that when we take large n, the difference between the two can become arbitrarily long. But here, before I discuss this problem, let me, I mentioned energy minimum and maximum, but I want to show now what is minimum and maximum of which theory. So this is a little bit the non-trivial part of the whole construction. So our proposal is that the deconfined phase is exclusively in the type 2A superstring, and it is a minimum of the free energy, while the minimum of the free energy related to the confined phase and the maximum related to the phase separating, they belong to M theory. So this rather means that there should be a phase transition between the two theories. And indeed, if we recall again this plot from Itzhaki Maldacena et al. In 1998, if this is correct, then this should be the case. So imagine that we are in a scenario when we push energies to be low. Then in the right-hand side, this would mean that we are going towards this direction. So then there should be a point, let's say here, that we transition from type 2A to M theory. And yeah, so we will see later how this point is related to this transition. So here in this slide, I'm showing the free energy with respect to the energy. And depending on when we are between the T2 and T1, the deconfined phase can be global minimum, or the confined phase can be global minimum. And one way to understand this is by this Polyakov loop here. So we see that we simulate at mu 0.5 near the transition temperature, and the proposal we want to show is that this phase here is a confined phase. So this should correspond to either this or this. While on the other hand, the deconfined phase is again either this or this. Now, suppose that the simulation is at this phase here. In order to go there, one has to overcome a barrier, which is this maximum. So therefore, the simulation spends way less time into this point here, which is furthermore unstable. Therefore, we can interpret the dip here as more rare configurations of the Monte Carlo simulation, and this should be the maximum. So again, we are in a first order transition scenario, and we want to understand now the difference T1 and T2. So T2 corresponds to a Gregory-Laflamme transition. And in a sense, Gregory-Laflamme is when a black string wrapping a circle as one here, after some temperature collapses to a black hole, which is localized into this circle. So one can imagine that this is the 11-dimensional circle. And this was, the initial work was from Gregory-Laflamme, but then later people studied more concrete examples, and the temperature happening for this particular case, for the T0 model, scales like n to minus 5/9. On the other hand, T1 corresponds to maximum confinement or minimum deconfinement temperature. And in order to get a rough estimate of this, what we did was to consider a Schwarzschild black hole in 11-dimensional case and consider its mass to be the Planck mass. Now, carefully doing the computation, one ends up with temperature to be to the power of n or to 1/3. So this rather means that T1 grows with n, while T2 becomes smaller and smaller with n. So the difference in a large n scenario would be rather large. And this is shown here. So again, to understand the whole picture, we want to build again motivation from ADS5 times S5, where we are in a microcanonical ensemble, and we fix energies and we study the model. So we fix energies and study what's going on. So again, by the review of Magoo and the work of Aharon et al., there is a scenario when one starts with small temperatures in a confined state, which corresponds to graviton gas. And as temperature grows, it hits a point when we see the onset of Hagedorn stream. Then there is an unstable phase, which is connected to small black holes localized along S5. And these small black holes, they are unstable because they have negative specific heat. So as temperature goes down, energy goes up. And again, there is another transition here, which this black hole grows and fills the hole S5. And then this can be seen as a big black hole sitting in IDS, filling the hole S5. But a very important ingredient is that this scenario takes place always in 10 dimensions. So having built some intuition from this IDS 5 times S5 case, now I want to show what we would expect for the P0 case. So this is a graph of 2 slides ago, where I want to claim that it could be possible that this free energy minimum, the confined phase here, would correspond to graviton gas, but in this case, an 11-dimensional graviton gas. Again, there should be at some point a signaling, a passing to an unstable phase, which could be thought as an 11-dimensional black hole localized along S1, which also has negative specific heat. And again, there is a transition to type 2A at temperatures T2. Now, this is understood as a Gregory-Laflamme instability in this case. So in our case, in the microcanonical case, where we fix energy, we have this rather speculative diagram. And it is speculative because we don't know the exact gravity details. So again, we have an 11-dimensional graviton gas. We have the unstable phase of 11-dimensional Schwarzschild black hole. There could be also another transition here by intuition, by the work of Horowitz and Martinez in '97, where we have an intrinsic transition from an 11-dimensional black hole to 11-dimensional non-uniform stream. And again, here at this point, there should be a transition from M theory to type 2A. And indeed, as we explained based on motivation from the conventional ADS-CFT, indeed, this could be the case, because by work from Sandborg in '98 and Aharoni et al., this transition here, it is likely to be a Gross-Witten-Wadia transition, which is furthermore related to a Gregory-Laflamme instability. It could also be another case, or maybe a similar to this could be also the partial deconfinement proposed by Berestein, Maldacena, and an incomplete list of people. And partial deconfinement simply means that it can be understood as follows. So the Polyakov loop can be written as this, as some phases, where these phases can be understood to run a compact circle. So the way that these phases distribute this line can be analyzed by this rho theta function. And when the distribution is, so here theta runs from pi to minus pi, okay? And when the distribution is uniform, we are in the completely confined phase. When the distribution becomes non-uniform and non-gapped, we are in the partially confined phase, while the transition from partially confined to completely deconfined, which is a non-uniform distribution and which also has a gap, it is known as Gross-Witten-Wadia transition. And here, partially deconfined phase simply means that when we have a big matrix, which is n by m, there could be a region there could be a sub-block of the matrix, which consists of m by m degrees of freedom, and it is deconfined, while the rest of the matrix can be confined. So this brings me to the summary of the talk. And again, going back to the beginning, we have observed the BFSS confined phase. And we propose to understand this confined phase as a Schwarzschild black hole in 11 dimensions. And furthermore, it could be possible to study this phase via Monte Carlo simulations, as I explained previously. Now, one caveat was that the BFSS simulation was not fully under control because of the flat direction problem. But on the other hand, BMN model seems to be better under control because it has the mass term. But again, to see if this claim holds, we should do much more precise comparisons with M-theory observables. And this is something that requires quite a lot of work. But of course, one simple example would be to just try to push to larger n and see and verify these results more rigorously. So with this, I would like to thank you very much for your attention, and I'm open to any questions that you might have.